Welcome everyone to the week 7 tutorial session of Galois theory MA70. Today we'll discuss some sample questions related to week 7 lectures. So let's begin. Uh, okay, so there is this summary which is also written on week 7 assignment. So let's just go through once because we will be using back and forth these theorems and results. Okay, so I'll choose some red color. So okay, so let L over K be a finite extension. So we always talk about finite extension, at least for this week questions. Then the order of Galois group Galois L over K is bounded by, okay, so what is Galois L over K? This is automorphism group of uh, automorphism group of K algebra isomorphisms of L. So we take all K algebra automorphisms of L, and what is K algebra automorphism? It should be a K linear isomorphism, and it should be a ring isomorphism. Okay, so there are two conditions whenever algebra comes. There are two structures on the set, which is one ring or field, whatever it is. So ring structure, and there is vector space structure. Okay, so corresponding to that we have ring isomorphism, and corresponding to vector space structure we have K linear isomorphism. Okay, so this is the Galois group by definition. Firstly, this extension L over K need not be a Galois extension to define this definition. So this is just a Galois group of the extension L over K. Okay, now so this is here, definition is there, and we in the lectures it has been proved that that cardinality of Galois L over K is always less than or equal to the vector space dimension of L over K. Okay, K vector space dimension of L. So, and we always assume this is a finite field extension, because this makes sense then only. Okay, L over K is finite. And okay, so this theorem is said to be the Dedekind Artin theorem. Now third thing is, so let L over K be an arbitrary field extension, so it need not be a finite field extension. The Galois theory centers around the natural operations. So as last time we have discussed how this operates on L. So sigma x goes to sigma x. So we have studied some questions related to action of a group on any set. So here we have taken field, and Galois L over K has been so this is the group we are acting on L. Okay, then we have 4 important statements. Let L over K be a finite extension. L over K be a field extension, and F belongs to Kx, then the Galois group operates naturally on the zero set of F in L. That means we have a Galois L over F, and you have the set roots. And so basically it says when you apply, so this sigma x, so it means sigma comma x is goes to sigma x. So whenever you take any element of Galois group, so any element of Galois group means you consider a K algebra isomorphism of L, then every root of x which belongs to L, um, every root of I should say fx. So you consider VLF. So uh, you consider a minimal polynomial, then every root will map to its other root of this set. So VLF is uh, f should be defined to be, okay, it's fine. So it operates in the sense that sigma x will always map to a root. So if x is a root of some polynomial f, then sigma of x will always be the root of the same polynomial. That's the that's this action says. Okay. Next, if L over K is a finite Galois extension, so if it is given to be a finite Galois extension, then the fixed field will always turn out to be K. So we are taking extension L over K, then fixed field of L will always be under this Galois group will always be K. What does this mean? So fix Galois L over K is equal to all those elements of L such that sigma of x is always be is going to be x for all sigma belongs to Galois group L over K. Okay, so we are just saying when you apply sigma on it, it is always going to be the same element. So we call it to be the fixed field of Galois L over K. Okay, so this is, and when it turns out to be K not bigger than that, K is always going to be there, but it could be bigger than that. But when it is exactly equal to K, so if it is a finite Galois extension, then it is always going to be K. Third, a simple algebraic field extension Kx over K is Galois if and only if. So we already say that this is a simple extension. If we assume that Galois extension is simple, then we are already having primitive element. Then so it will be set. It will be a Galois extension if and only if the minimal polynomial of x in Kx splits into simple linear factors. Simple linear factors means, firstly it should split, second it should split in different factors. So it should not be like alpha x1 square. So it should not be there are repeated roots. We don't want that. If it has repeated roots, then it is not going to be the Galois extension. So in particular, so this is the this should be minimal polynomial for should split, and the cardinality of this zero set should be exactly equal to n, which is kx over k. And yeah, so it should be there. So yeah, I missed this line. L over K is called a Galois extension if the equality holds. So we said that this is cardinality of this Galois extension is always going to be less than or equal to L over K. And now we are saying this should be cardinality of Galois of this Galois group. If it is equal to L over K, then the extension will be the Galois extension. So that is the definition. Any doubts in these theorems results? Because we are going to use many times these theorems. Okay, great. So yeah, and finite Galois extension are simple. That is, there exists a primitive element. Yeah, if it is a finite Galois extension. So the extension is finite, that is L over K is some finite number, and if it is a Galois extension, then it is always going to be simple. That's in each step we just only this step has if and only if condition. So you cannot say that if fixed field is K, then this is a finite Galois extension. At least for now we cannot say, because these are just direct implications, not if and only if implications. Is that okay? Is that okay?
Yes.
Yeah. Okay. Okay, so let's try this first question. Prove or disprove. If L over K, L over C is a finite field extension. So it is given to be a finite field extension. Then, so we have to check L is equal to C. So like this is a question to check. I wrote. So you have this extension, and this is finite. So finite means so L over C is is less than infinity, some finite number. Okay. So what do you think? Like, is this true that L has to be just C, not something bigger? Okay. What your intuition?
Yes,
Yeah. Yeah.
yes, ma'am. It's true.
Okay. It's true. Okay. I agree with you. Can you explain?
Ma'am, it's a finite extension, so it's algebraic.
Exactly. Yeah. So this is a finite extension. So this will be algebraic. That we have already
That means
proved. Um, yeah. Then,
uh,
see,
then every element of L satisfy a non-zero polynomial in CX.
exactly. So,
But
hmm,
CX is already algebraically closed field. So it also contains that element of alpha which is in L.
okay, so you started with an element of L. Then we know that kernel of. So, firstly, everyone agrees that this is algebraic because we have proved that if it is a
Yes,
finite
yes.
extension,
Finite.
yeah, exactly. So, if it is a finite extension, then it has to be algebraic. Now, if X belongs to L, this implies a kernel of the this evaluation map of X in C. Okay, base field is C. This is non-phi, like non-empty. So there is some element exactly as she said. There this implies there exists a non-zero polynomial, and even more, yeah, non-zero polynomial f belongs to Cx. So the coefficients will come from C, okay, such that f of x small x will be 0. Yeah. So now what can we do? Yeah, so we have this fx. Yeah, I agree. Now,
Uh, if you use the fundamental theorem of complex number, it is algebraically closed, so that X is also belongs to BC.
yeah, fundamental theorem of algebra, I think. Yeah. So,
Yes,
yeah,
ma'am.
exactly. Very good. So, by fundamental theorem of algebra, this f, so we are saying x belongs to L, and even we can start with something like let's say if so even let L over K be so firstly we have this, so for every maybe uh, let x belongs to C and not in L minus C. Okay, so let's take it is outside C. Then kernel is this, and this implies there exists a non-zero polynomial f such that fx is equal to 0. By fundamental theorem of algebra, fx splits completely, or maybe uh, okay, yeah, fx, it's fine, fx splits in linear factors, okay, or in particular minimal polynomial of x over c is equal to x minus x, because if it splits in linear factors, then one of the factor has to be some x minus x, right? So because we are saying this splits in linear factors, so the minimum degree it could have the irreducible one. So this is always irreducible or prime. Okay, even we take Munich, so this is a prime polynomial. Okay, this is a prime polynomial, so this will always going to be x minus x, because it splits in fx splits into linear factors, so minimal polynomial we can have to be that factor only. There is no bigger degree we can have, like uh, it is the irreducible one. So if every fx splits, then the irreducible part will be for x will be x minus x. But this implies mu xc, which is x minus x, this belongs to cx, or maybe I can write here only cx, and but this implies x belongs to c, which is a contradiction, or maybe it's better to write like this. That's nice, yeah. So but this implies that x belongs to c. This implies L is contained in c, and since L is an extension of c, this should be equal. Very good, yeah. Is that okay? Any doubt?
Doubt.
Yeah.
There exists non-zero polynomial kernel up to that point. All right, but by fundamental theorem of algebra, if it splits into linear factors.
So by fundamental theorem, what does fundamental theorem says? That every non-zero polynomial in Cx has a root, right? So
Yes.
fundamental theorem of algebra says every non-zero polynomial in Cx has a root in C, has a root in C. And this actually, if and only if, like you can write, every non-zero polynomial, by induction you can even prove, every non-zero polynomial in Cx has all its roots in C. That means has all is splits into linear factors. Linear factors in C, or all the roots are in C. So every polynomial, like all the polynomials in Cx has roots in C itself, all the roots. So we don't need to ever go to extension for it. So this actually says this is a algebraically closed field. So we are required to just use maybe this. So this property says that this is algebraically closed field. That means it is every polynomial in Cx splits completely, like splits into linear factors in C. That is we know from the fundamental theorem of algebra. And from that, what do we know? Here fx, whatever we have taken fx, that has to split in linear factors, right? And we know that kernel is generated by the minimal polynomial, and minimal polynomial will divide fx. So minimal polynomial so in this step, this minimal polynomial mu xc will have to divide f, right? So if this divides f, and we are saying this splits into linear factors, then one of the factor has to be x minus x, right? Because if these are linear factors, maybe some square of it, we don't care, and you can have something else also, let's say y, and whatever, you can have more than that. then but mu x c has to be the that factor which has only x and irreducible one, so it has to be x minus x, right? The least one. So mu xc has to be x minus x, and what does this mean? X belongs to c, because x minus x minimal polynomial is in cx, so x belongs to c, it cannot be outside that. And
Exactly.
this is in cx, it splits in cx itself. Yeah.
Okay.
Okay, great. Okay, so this says you cannot have any finite extension of c.
Ma'am, what is the significance of this question?
Okay, so significance of this question is like you cannot even have any finite extension of any algebraically closed field, like which just splits in itself. So but there could be infinite, so there are some infinite extensions, infinite field extension. You can have infinite field extension, and that you also know, like you can take x1, you can always has in indeterminates, even you can just take this, right? Because this is infinite, you agree, this is indeterminate, because 1x x square, there is no polynomial you can make, so this is an infinite field extension. So it's just significance is basically there is no infinite extension of any algebraically closed finite extension of algebraically closed field. That is something you can remember. Yeah. Okay, so let's try second part. For a prime number p, the field extension fpx over fp x raised to power p is Galois. So this is prove and disprove. We don't know if this is correct or not. Let's try. So this is right. Let's try this b part. So b part says to check fp x over fp x raised to power p is Galois. Okay, for some, for any prime p. Okay, p is some prime number, so is this a Galois extension or not, we need to check. Okay, so again, what do you think? So this is the extension. It's better to write like this to understand. Okay, firstly tell me, is this finite or infinite extension?
Mm,
Sorry?
finite manner. The extension is full.
Exactly. So how will you say that? This is a finite extension, but yeah. How should we infer?
Uh, why it's finite?
By?
No, what's your question? I did not get.
Yeah, I'm asking. So my question is this a finite extension or not?
Yes, yes, ma'am, because it is an extension of a finite field. So, no, sorry, sorry, of field of finite characteristic.
Uh, yeah, but still we cannot say this is not a finite. This is not a
Yes, ma'am.
finite field. Not a finite field, because this is indeterminate, so x is indeterminate. To say that this is a finite field, you should have finite number of elements, but in the set you will have something like a plus you can so you can have, let's say, a0 plus a1 x raised to power p plus a2 x raised to power 2p Okay, so square of that, and you can have all the powers of x, of multiples of p, right? So you can have x raised to power 3p, some am I writing it right? So x raised to power p into x raised to power p. So you can, so this is a field. So you are allowed to have multiples, right? So you can have x raised to power p into x raised to power p, which will be x raised to power 2p. Similarly, you can have, and you can have all the linear combinations. So you will have all these kind of elements. So this varies, like x raised to power 2p, you can have more options, because this is indeterminate. You cannot make it small. Of course, these coefficients are coming from fp, so these have finite choices. But you can have, let's say, polynomials. So this is some finite polynomial, uh, finite polynomial finite polynomials in, not finite, I don't need to write. If I'm saying polynomial, it is itself a finite sum. So finite sum, okay, polynomials in, let's say, 1 x raised to power p, x raised to power 2p, and so on. So the cardinality is not going to be finite, because you cannot say these are same also, any of these.
Yes, ma'am, I get it. Ma'am, also, basically the extension is the dimension of the vector space world.
Exactly.
So xp belongs to be the ideal x. So the basis is, so it has a finite extension. We can write 1x x square. The base field is contained in, because every element is up to x to the power p minus 1. So it has an extension.
Exactly. Very good. Yeah, exactly. So you can always write uh, one. You can generate this extension, or you can generate fpx over fp. Or I can write in a better way. So basis of course, fpx over fp x raised to power p is, you can generate it by 1 x square up to and so on x raised to power p minus 1, because you have, so any typical element of fpx will look like of some uh, ai x raised to power I, where I belongs to, let's say, some subset of mm, I belongs to, let's say, subset h, subset of natural numbers n. Okay, some finite set. So every element will look like this, and where ai's belongs to fp. And now, so any polynomial you can write it, so now you are allowed to have fp x raised to power p. Like you can have, if it is a multiple of, so for example, if it turns up that x raised to power p plus 1 you have, then you can write it x raised to power p into x, and x raised to power p belongs to fp x raised to power p. So as a basis you can generate with this, because if you have higher powers, then you can just avoid these x raised to power p ones, and then you can get this, right? So you can have x raised to power p plus 1, you can write with coefficient in fp x raised to power p into x. So this will generate, this is one of the bases of fpx over fpx raised to power p. So this is indeed a finite extension. Is that okay for everyone? Any doubt? I can explain again if you.
No.
Okay. Okay. Great. Yeah. So we know that this is a finite extension. Okay. So we can use those theorems and everything to conclude that this is a Galois extension. But firstly, what do we have? We have fpx over fp x raised to power p. So if we want to see that this is a Galois extension, so as I said, in this part, I'll just remove all these lines. So in these theorems, we only have this one to use, because if we want to say that this is a Galois extension, we have to say that because we have if and only if condition in this part only. So and this is a simple extension because that is fpx. So you can think of this. So fpx, you can think of this as, if I say this is k, so this is fpx raised to power p, you have the base field. Now you attach x, so this is like kx, or you can, let's say this is l. So this is indeed a simple extension. Simple means there should be just one element, primitive element, so that you can write L as kx, where k is the base field. So because these are same, doesn't matter how you are writing. So I mean fpx and fpx raised to power px are same, because whether you write like this or this, these are same. So this is indeed a simple extension. And we have also seen that this is a finite extension. So this is simple and finite extension. So we can use this theorem. Okay, a simple algebraic extension. So simple algebraic field extension is Galois if and only if the minimal polynomial mu xk in kx splits into simple linear factors. We don't need finite for to say this, but anyway. So simple algebraic field extension, okay, we have to prove algebraic, but this is finite, so this is algebraic also. Okay, even we can prove it separately that this is algebraic. I'll do that. If and only if the minimal polynomial of x, this primitive element x, splits into simple linear factors, that we need to prove. That this splits into simple linear factors means the factors should be distinct. That means all the zeros should be distinct, and it factors in linear polynomials. Okay, let's try to do that in lx, like in the main field. In the bigger field, it splits completely. So let's try to prove this, and prove or disprove, whatever, I don't know. Let's see. So firstly, I'll prove that this is algebraic. That is not required if I already said that this is finite, but anyway, we can prove that this is algebraic. Anyway, we need the minimal polynomial. So yeah, okay. So we have this. So I am writing kx and k, where k is fp x raised to power p, and this is fpx. Okay. Now or any way you can write, that doesn't matter. Now, so for this morphism we consider, so this is L. So L, I'm choosing variable to be z, some indeterminate we use for this epsilon map. And now we will try to find the, so what is the primitive element? Primitive element is x, capital X. So we are trying to have the map evaluation at x, and the base field is this is k. Base field is k. So this map we are considering, and of course we are mapping in L. Okay, so this, from this map, what do we have? This evaluation map we always do. So we have kz, and this is mu x. So x is capital because and this z is indeterminate. So k, this is k algebra, isomorphic sk algebra with k x. So this is actually L. So we have this. Okay, so we need to see that. Firstly, can you tell me any polynomial which is so any polynomial f in kx in kz, find f in kz such that f of x is 0. Can you tell me any polynomial which is in kz and f of x is this x, okay, this capital X. So to be precise, z is your zp, sorry, not zp, fp x raised to power p, and you have some polynomial notation. So this is variable fx is equal to 0. So just think about which polynomial you can take such that f of z is equal to 0. What polynomial I can take here? And coefficients are coming from fp x raised to power p.
Another capital Z to the power P minus small x to the power P.
Exactly. Yeah, you said this, no? Yeah, this. Yeah.
Yes, ma'am.
Yeah, this is correct. Very good. So yeah, fz you can take it to be z raised to power p minus x raised to power p. I'm not saying this is minimal or whatever, but I'm just trying to say find a non-zero polynomial f such that fx is equal to 0. Now you can see also the coefficient should be from fp x raised to power p. So as you can see in this polynomial, coefficient is 1 and you have x raised to power p, which is there like in fp x raised to power p, even more precisely minus x raised to power p. These are there in fp x raised to power p. So we are good. So these coefficients are certainly in fp x raised to power p. So this is indeed a polynomial in fp x raised to power p such that fx is equal to 0. Now if you evaluate at x, you will get x raised to power p minus x raised to power p, then it will give 0, and this is a non-zero polynomial because z is a indeterminate. So don't be confused by x, but x is now a small x kind of thing, okay, but it has no relation. That's why this is a indeterminate, but in the base field itself you have x raised to power p. So you can have such a polynomial, right? All of you agree?
Yes, ma'am.
Okay, great. So now let's see if minimal polynomial is this or not. Okay, because we need to see that if minimal polynomial is splits in the bigger field and everything, although we can say from here itself, but just calculate what is this. This x is capital, of course. So what is the minimal polynomial? Firstly, this f should divide this minimal polynomial because you know that kernel is generated by the minimal polynomial. Since kernel of this map is generated by mu xk, we must have f should divide this polynomial. And what does this imply? Yeah.
Minimal polynomial divide f.
Oh, right. Thank you. Yeah, exactly. Yeah, minimal polynomial has to divide. Mu xk should divide f because f will be because it is generated by mu, so it should f is in kernel, so mu should divide f. Exactly.
Yes.
Now you know that degree of f is, so let's see. So degree of f is p. Now we need to see if any smaller polynomial or any other polynomial could be a part of this or not, like could be mu xk or not. Okay, first thing, you have given that f is x raised to power p, z raised to power p minus x raised to power p. Okay, now I am doing something. So firstly, you can write this as z minus x raised to power p because you know that power p, like whenever you have fp is of the characteristic is p, so you can write z raised to power p minus x raised to power p in as z minus x raised to power p. I am of course in the bigger field, okay. So basically you have kx itself, so mm because the coefficients are now not in k, because you have x, so or maybe let me write in some splitting field of f, so which exist of course, so of f exist because of Kroneker's theorem. So we know that from Kroneker's theorem that there will always exist a field where every polynomial is split. Like there will exist a
Such field.
field. Yeah, such a field. Exactly. So now you can write f to be z minus x raised to power p. But what does this mean? You have something like, you are saying in that field at least, that this is z minus x raised to power p. But you are always in, should I say that? Yeah. So you know that if f is a field, then f of x is a UFD. Yeah, if f is a field, then f of x is always a UFD. So there is no other factorization we can have, right? We also know that. So mu xk is going to be some power of this for some r less than p, less than or equal to p. Okay, even it could be more than 0 cannot be the case, even 1 cannot be the case, but okay, we will prove that. Okay, at least it will be 1. Okay, or maximum it can be p, because mu xk has to divide f, so it could be some factors of f in the in the bigger field of course, but at least it could be like this. But this has to be in kx of course. So we will check that if the coefficients of when the coefficients of z minus x raised to power are in kx. Okay, do you agree?
Please repeat one.
Yeah, so I am saying, so I started with, you know that mu xk divides f, and now and degree of f is p. Firstly, f is some z minus x we can write f to be z minus x raised to power p in some splitting field, at least in even in what do we say, okay, so in some splitting field you can always write it to be z minus x raised to power p. Okay, and I am saying we are always in the field, we cannot have different factorization of a field, of a polynomial, because coefficients are coming. Yeah,
It
sorry.
is a UFD
Yeah,
factorization.
yeah, exactly, it is a if f is a UFD, then f of x is always a sorry, f is a field, then f of x is a UFD, because f is also a UFD. So now what do we have? Yeah, so this is always true. So we have f is equal to, so we cannot have different factorization of a polynomial. So I am saying f splits as z minus x raised to power p. So it will split like this only in any extension, or it will split like this. So what does this mean? Mu xk, which is in kx, will be some part of this, like z minus x raised to power r, because what are all the options? It could be some less than p. What I mean to say, so mu xk will be some part of f, like some factors of f. That is the only choice it could have, right? So mu xk divide f means mu xk has some factors of f, right? Has exactly some factors, like there could not be any other.
Yeah.
So from this we know that since f is factored as z minus x raised to power p in some suitable field, so mu xk will be some z minus x raised to power r. That only it could have, because it is just the repeated factors. So we can have some factors of it, or maybe all, we don't know, that we need to check.
Okay.
Okay, now let's see what is this. Now if we are saying mu belongs to kx, that means all the coefficients are in kx, all the coefficients are in k. That means firstly we can split this up as okay, I can write in terms of summation. I am using binomial theorem, so you have rc k z raised to power r x raised to power, sorry, z raised to power k,
Z raised to power r minus k.
and there
Sorry.
is minus 1
No,
raised to
so-
power, so minus 1 raised to power k, yeah, over k. So k will go from 0 to r. So from binomial theorem we have this factorization. Now in this factorization you can see that we don't care what the power of z is, because z is the variable that we need a polynomial. Sorry, I should not write like this. So we have x, and this is kz, right? Polynomial is in z. Okay, so this is in kz. Now what does this mean? The powers of x's are important, because what we want, we have this k equals to 0 to r minus 1 raised to power k, r c k, you have x raised to power r minus k, and z raised to power k. So what do we want? This should belong to k for all k, right? This coefficient should belong to k, but this is just a number, so we don't care, because this will belong to fp. But we are concerned about this part, x raised to power r minus k. But when will it be there? When will be the x raised to power r minus k belongs to k? K is uh, k is your fp x raised to power p. So we know that we cannot have lesser power than p of x. So r minus k has to be p. That means, so this implies only for r minus k to be p or 0, we can have x raised to power r minus k belongs to k. But what does this mean? When will this happen? So this implies z minus x raised to power r should be equal to so this should be r choose 0, and this will be 1, x raised to power r, and there should be minus. Oh, okay, have I wrote wrong? So yeah, the formula should say, or maybe I can write r minus x. Yeah, anyway, so you will get this to be minus, this to be plus, r choose r, z raised to power r. So only in this condition you can have this. And when will this happen? So all of these has to be 0. That means all the coefficients has to be 0. That means what? That means we cannot afford the other x raised to powers. So this implies r has to be exactly p, because then only we can have something. So this equality holds. This equality holds when r is equal to p. It cannot be at any other step. Is that okay? I could have explained better, but I think this is okay. Is that okay? So what we are saying, we cannot have the other powers of x. That's the main issue. We cannot have powers, or maybe we can start with this also. So let r is strictly less than p. Okay, then what will happen? This has to belong to, or I could just say this belongs to k, but but that is a contradiction, right? For r less than p, this is a contradiction, so this has to be p. Is that okay? Because when you expand it out, you will have some lesser degree terms, then you will be in trouble. Because okay, so okay, wait. In that explanation itself, you can imply this. Okay, so what I mean to say, so this part has to be 0, right? R choose k has to be 0. But when will it be 0? When it is divisible by, this implies that this is divisible by p, because r choose k is never 0, right? So it has to be, it is 0 in fp. That means p should divide r choose k. But when will it happen? This will happen only for only if p, because p is prime and r is, since that you can easily check, since p is prime and r is less than p, or yeah, r is less than p, this is not possible. Not possible. Of course, we want it for k is from 1 to r minus 1, because those are the problems, like, because if k is equal to 0, then we are okay, because x raised to power r also we don't want, but that's okay, and r is equal to 0, that also we don't want. If k is equal to r, then it is okay. So let me write like this. You allow 0 also. Okay, so it's fine. So what I mean to say, if you have choice for r to be r is less than or equal to p. Now you take this expansion of this expansion z minus x raised to power r, then you have this binomial expansion. Now what do you want? You cannot have some lesser power than x raised to power p. So what does this mean? You cannot have these powers unless k is equal to 0, right? In this case, if r is strictly less than p, then you will have a problem. But you know that p cannot divide the coefficient unless this is not possible for r is, yeah, this is not possible because r you have chosen to be less than p. So let's assume that r is strictly less than p. So this is just back and forth argument. I think it is clear, because if you take less than p, then you will have a problem with the coefficients that cannot be 0, because it will not be a multiple of p, and because of that there will be some powers of x which are strictly less than p, and you are done, like you cannot have that. Is that okay?
Okay.
Okay, great. So mu x k is equal to x raised to power p. So we want, so I am writing exactly in the form of z raised to power p minus x raised to power p, which of course belongs to kx. Sorry, kz. That is your variable, which is fp x raised to power p z. Very good. Now what do we have? So this is your minimal polynomial. So this implies degree of the extension L over K is P, because that should be the degree of mu xk. Okay. So you have that degree this extension is this. But you have seen this is equal to z raised to power p minus x raised to power p in, of course, kz. Now for Galois extension, what do we need? For Galois extension, extension, we must have, so that is a if and only if condition, we must have mu xk splits linear into linear factors in L, and roots zeros are simple. Simple means there are no repeated roots. Zeros of mu xk are simple. Okay, so there are two things. Firstly, and of course, L is fpx and k is fpx raised to power p. You have this. So it splits into linear factors in L. So now let's see if that is true. This is equal to z raised to power p minus x raised to power p. You can write this here. Can you write this in? So I should not write this. So that is not in same line, but this is equal to z minus x raised to power p in L. So this splits into linear factors in L. Why I'm saying that? Because you know that coefficient should be there. So x is there, right? In L is equal, what was L? So in L means coefficients are in L. Okay, that is fpx. Because L is fpx, so coefficients are there. So it splits completely. This implies mu xk splits into linear factors in L. But second thing, what do we need? What is the second thing we require? We need simple roots. We need zeros should be simple, so it should be distinct. But is it the case? But mu, so I can write even in that sense, v of mu, so the set, so zeros of mu xk in L is just x. Is that okay? Because there is just one root, it has repeated roots p times, so x is a repeated root, and its multiplicity is p. Is that okay? So this is the notation for zeros of mu in L, zeros of the polynomial mu xk in L, which is just one element, which is x, because you have this polynomial. What are all the roots? It's just z minus x.
Okay.
Yeah, and that is the problem. So what do we need? Simple. Firstly, it should be simple roots. It should not be repeated. So this cannot be. And so the other condition you can check. So VL, the cardinality of this should be same as, so any notation you can use. Cardinality of this should be same as degree of mu. So that is the requirement, right? But that is not the case. So L over K is not Galois. Yeah.
Linear factor does not depend on multiplicity.
Yeah. Linear factors does not depend on multiplicity. So first thing is this. Second thing is this. We need two conditions. So we can go there. So that was the requirement. So it says, yeah. So it says simple linear factors. What does this mean? So simple linear factors this with cardinality of xi. So xi's are the roots. Okay. So this cardinality of this set should be same as n. N means degree of mu, because you have seen this degree of mu is n. So that should be exactly n. So this set will have just one element if all are repeated. So x1, x2, everything is same as x. So this cardinality is just 1. But we require it to be p in our case, like whatever the degree of mu is, which is equal to kx over k. So this degree of mu x should be same as the cardinality of the set of zeros, but that is just 1 in our case. That's why this simple appears. Simple means there are no repeated roots. If there is any of the repeated root, for example x1 is same as x2 and all other are distinct from x1 x2 even, so but x1 and x2 are same, so the cardinality of x1 to xn, this set will be n minus 1. So then again is a problem. So we want all the roots to be distinct.
Okay.
Yeah, so that is the requirement for Galois extension. Okay, so this property fails and we are done. Yeah. Okay, great. So let's try the third part now. So the second is wrong. Third is, let k is equal to q root 2 and L is equal to k root 3. Find basis of the q algebra k. So I'll just copy this. Okay, I'm just talking about the C part. So let k is equal to q root 2. I'm not saying this is correct or not, but C part. Let k is equal to q root 2 and L is k root 3. So this is a next one. So we have this kind of figure. So you have q, okay, rational numbers. You have q root 2, which is said to be k, and then you have k root 3. So this is actually what? This is L by definition, and this is what? Q root 2, and you attach root 3 also. So root 2 and you attach root 3, and these are like, this is same as all the elements containing root 2 and root 3. So these are same. Okay, smallest field containing root 2 and root 3 and q. So this we have the picture. Now question is find basis of, so first is find basis of the q algebra k. So firstly let's find this basis. Q algebra k is q root 2. Okay, so what will be the basis? A basis at least, can you tell me? So this extension we are asking. So this is k. What will be, just give me a basis, because this is vector space, right? We just need vector space basis. So how can you write all the elements of q root 2 using q?
1 and root 2.
Exactly. So we can have k to be a plus b root 2, where ab belongs to q. And also one more thing, we like root 2 can be rationalized, and this is algebraic also. So this will be same as this root 2, because you have a equation, right? X square minus 2 you can consider. So this is algebraic also. So square bracket is same as small bracket, and this is k, and also this forms a basis, not just a spanning set. So you have 1 and root 2 as basis. Can take basis to be this. Very good. Next, the k algebra L. So we have basis of k algebra L. So we are talking about q. So firstly I should write in this form only. So you have K algebra, L. So L is K root root 3, and which is say, so we don't care, okay, we care of course, Q root 2 root 3, and this is Q root 2. So this is the extension. So you have root 2 already attached, now you are also attaching root 3. Okay, so what do you think, what will be the so yeah, what will be, firstly, uh, okay, so what do you say, what is the basis, a basis?
Now, if we write the element of L as we ever write the element of K, so it will be A plus B root 3, where A and B is an element of Q root 2.
Yeah, exactly, that is true.
Then,
Yeah.
then, yes, ma'am. Then we again write A and B as an element of a Q root 2.
Right, we can write, of course. So let's write this out. But we need over K, that is, we need to understand also. We can write, of course. So yeah,
Yes, ma'am.
we can write maybe A1, A2 root 2, and you have B1 plus B2 root 2 root 3. So all AIs and BIs belongs to Q. Right, we can do that, of course, but the base field is Q root 2, so we are allowed to have linear combination with coefficients K, that is Q root 2. But one more thing, so this is fine, but this is not required here, uh, but this is okay. But one thing is there, you have to check that root 3 does not belong to Q root 2, because if root 3 belongs, then this cannot be a basis, even extension will be just of 1 degree. That looks easy, but looks, of course, yeah, that should not be there. But we can also check that, right? If root 3 is of the form a plus b root 2, because we should prove everything rigorously, because in place of 2 and 3 we could have other options also. For example, if it is given that you take 8, for example, in place of 3, if we would have 8, then then the extension will have degree 1, right? Why? So what I mean to say, if for example you have given root 2 and you have given root 8, then what will be the degree? Is that okay? Do you agree? The degree is 1. That means I'm saying these are equal.
Yes, ma'am. If we cube square root 2, then it will be root 2.
Exactly, because square root of 8 is 2 root 2. So we can obtain this from Q root 2 itself, right? So this is not a new element to deal with. So in particular, you could have some notations like root P and root Q. So P and Q should have some relation. Q should not be a multiple of P or something like that. So at, actually the P and Q should be relatively prime, not just prime or some multiple. We are saying these should be relatively prime. So that means GCD of P and Q should be 1. That is a requirement we have. So when you do this, you should prove it, like this does not. So let root 3 belongs to Q root 2. This implies root 3 is equal to a plus b root 2 for some. So let me do it for some general P and Q. So let's say this is Q, this is P. These are not primes, I'm saying these are some numbers, or if you want I can choose it to some other. where P and Q has GCD 1. Okay, I'm not saying not necessarily prime. Okay, distinct primes. So you have root 2 QB to be equal to A plus P root P for some AB belongs to Q. Now what can you do? Let's say Q A plus B root P, and you will have a square. This implies Q is equal to A square plus PB square plus 2AB root P. Okay, now you will have Q minus A square minus PB square is equal to 2AB root P. Now how shall I check? Even we should why should we do this? We can even from here, yeah.
Uh, since root 2 is belongs to the Q root 2, so the field generated by Q root 2 is contained. So we apply the multiplicity of the order.
Multiplicity of the order. Sorry, I didn't follow. So what you are saying?
From starting, if we assume, if we prove it by other way, that if the since root 2 belongs to the that field, so the field generated by Q of a root 2 is contained in that bigger field.
Yes.
No, which is prove, suppose let root 2 is belongs to the.
Okay, let root 2 belongs to.
That one. Root Q belongs to the Q root P.
Okay, Q root P, right? Yeah, if we assume this, right, then.
So the field generated by Q root P is contained in. Okay, yes, and if we have a tower, Q root P and contentment.
But this could be same, right? That's what we need to that's what we need to prove. Like, so for example, as I considered this case, so yeah, so for example, if we had 8, then these are going to be equal. Either they will be equal, either the other option is like if this does not belong to Q, then the extension could be of degree 2 only. There is no other possibility, of course, like either 1 or top 2. So we just need to check whether they are equal or not. That's the only thing we need to check. So if, for example, if P is 2, then these are equal, then we are good. Okay, these are equal. So but we for this case PQ is equal to 1. I'm just trying we are trying to prove it rigorously that this is not if P and Q are relatively prime, then Q root P Q root 2 is not going to be contained in root Q is not going to be belong to Q root P.
Yes, ma'am. Okay.
Yeah, so yeah, what you are saying exactly, this is true, because even root 2 and root 3 we can intuitively see that. Even here also we can think of that, but I'm just trying to write it rigorously that this won't be the case. So if someone asks like what is the condition when root Q will not belong to Q root P, all the conditions just if question is like that, then we have to prove that whenever P and Q are relatively prime, that then root Q will not belong to Q root P. So like that, if and only if condition. So like in this example, as we have seen, so Q should be equal to A square plus PB square, and 2AB should be 0. What does this imply? Either A is equal to 0 or B is equal to 0. So if A is equal to 0, then Q is equal to PB square. This implies P divides Q. Okay, that is a contradiction because P and Q are relatively prime. So we sometimes write GCD or not. That is like this is same as GCD of this is just we don't write many of the times. So GCD of P and Q is 1, and if B is equal to 0, then if B is 0, then Q is equal to A square. And if q is equal to a square, what does this mean? Q divides a, of course, but then actually we are done. If q is so this implies root q
But
belongs
not
to q, which is also not the case, right? I should say relatively prime, and there is one more thing I should say. Not necessarily so p and q are relatively prime and square free. Okay, it should be so this is not if and only if condition again, because you could have 2 root 2, but you can always identify it with root 2. Like for example, if you have root 8, you can also write it root 2, because root 8 is 2 root 2, so this will be same as q root 2, right? As a field. So there are two conditions. Firstly, p and q are relatively prime, and p and q are square free, and of course and absolute value is not 1. So basically, what does this mean? P and q are not 1. Okay, three conditions. So p and q are relatively prime, p and q are square free, and p and q are not equal to 1 or minus 1. Is that okay? So this is a general statement.
yes, ma'am.
Okay, great. So yes, yeah, I can. So okay, so we have this. Now in particular, this in particular, root 3 is not does not belong to q root 2. So that was something we needed to prove, this one. So basis of k algebra k algebra L will be what? Then we can say that L is equal to a plus b root 2. If it is not 1, then second option is 2, and 2 is there, like we have a basis, right? So basis should be 1 and root 3 of L over k. If it is not 1, because root 3 does not belong to k, so it has to be at least 2, and we have seen that 2 is working fine. Is that okay?
Yes, ma'am. Okay.
Okay, great. So third part is, so next one, it is asking q algebra L. So basis of q algebra L. Now double we are going. So now it is asking basis of q algebra L. Yeah, KL. Yeah. So where L is q root 2 root 3, which I can always write it as q root 2 comma root 3, and you have here k, which is q root 2, and you have here q. So they are asking about this. Okay, and you have seen that this is 2, this is 2. So what will be the dimension from this formula? So that, sorry, not k, as we have found the basis, we know the what are the degrees, right? So we of intermediate field, so we can write it to be this, and this will be equal to 2 into 2, which is 4, right? Is that okay? Of course this is finite, so I can use it.
Fine. Okay.
Yeah, there are other ways also to say that, but yeah, right. Okay. Um, yeah, this formula makes sense if L over Q is finite, which is true, of course, because root 2 has a minimal polynomial, root 3 has a minimal polynomial, so you can get it. Okay. So second thing is, and what is the basis? A basis. So as you have seen, since we also know root 3 does not belong to q root 2, and so basis you can take it to be root 2, root 3. And so if you want to ever find the basis and if you know the dimensions, you can just consider the so this is a way to do that. So shall I say, if I call these bases to be, let's say, of b l over k, and you call it to be b k over q, then this will be x into y, if where x belongs to basis k over q and y belongs to bl over k. This is also true always, because you have this formula and you can get it all the basis elements from here. Since this is 1 and root 2, and this is 1 and root 3, so basis will be just 1 multiples 1 into root 2, so 1 into 1, 1 into root 3, root 2 into 1, and root 2 into root 3. So this will be the basis. A basis are. Is that okay?
Okay.
Yeah. Okay, great. Now let's see the next part. So find the minimal polynomial of root 2 plus root 3. And next it is asking, is the field extension L over Q a Galois extension? Okay, so let's try to do that. Okay, so again I'll try to prove. Okay, no need. Anyway, so you can have, so what is the minimal polynomial of root 2, minimal polynomial of root 2 plus root 3 over q? They are asking this. Okay, that we need to find, and then we need to check that if this extension Galois or not. Okay, so let's see this. Firstly, what is the minimal polynomial of root 2 plus root 3? So what are your guesses? So again I can make this tower. Yeah.
If we put x is equal to, oh sorry, root 2 plus root 3, okay, x is equal to root 2 plus root 3, and we take the root 2 or root 3, any one of them take as single side of x, and others after that
Okay.
we put square it.
Okay, so we get this.
Now we have take the root term another side and again square.
Yeah. So yeah, this is of course very good way. Yeah, nice. So we have a polynomial like this. So you will have 8 and x is to power 4 plus 1 minus 2x square is equal to 8x. Oh, we did some mistake, I think. Yeah, there will be square. Yeah. So we will get this is minus, yeah, 10x square plus 1. Yeah. Yeah, this is one polynomial. We don't know if this is a minimal polynomial or not. Okay.
We can check it is irreducible. Is it irreducible, monic, and
Yeah, this is monic, but
yeah,
we need to check if this is irreducible.
irreducible. Yes. Irreducible.
Q.
If I can take two. So two, it shall not be follow Eisenstein's criteria, because 2 does not divide 1, and 2 and
But this does not divide 1 also, no?
uh,
I think the requirement was p square should divide the constant term and p should
p square. Sorry,
this is one, so we cannot use that for any p. Yeah.
P divides all AI excluding
The
x n mean leading term.
yeah.
Here leading term 1 and p square does not divide a0. A0 means here 1.
Right, but we have one, so we cannot have p divides a zero. That
Hmm.
we also require, right? For
Hmm.
Eisenstein. So we cannot say from there.
Uh, this polynomial is it polynomial over q
Mm-hmm.
rational number?
Hmm.
So here I can check if it is as a root pyq, then p must divide 1 and q must divide 1. Uh,
Right. So for roots, that is okay. Like, so for example, as you said, of course. So over q, it will not have any root. Even to say that this is a reducible over q, and even for z, that is same. So it will not have any root in q, because yeah, as you said, this should divide this vector, and there is this rational root test, right?
mm,
But that is not enough. So it could have factors to be like square and square, right? There could be factors like square and square, and of course, this extension has degree 4. So and q is contained in q root 2 plus root 3. Okay, there is this in between, and it is contained in q root 2 over root 3. So this is 4. Okay,
yes.
so this is 4. So this extension could have 2 or 4, right? Or 1. Firstly, 1 cannot be the case, because root 2 plus root 3 does not belong to Q, right? So
Uh,
1 it cannot be 1, but it could be 2 or it could be 4. That is
if it is 4, then q root 2 plus root 3 and this tire it must be 2. Then
yeah.
if we multiply 4 into 2, that exceed the number dimension of the q over q root 2 comma root 3.
Exactly. So to say that 4 means irreducible. 4 means this is irreducible, right?
Hmm. Hmm.
And 2 means it could be possible that there are some multiple of squares. So what we really need to check that this is not a reducible, this is so I am actually claiming that this is a irreducible polynomial, but for that, what we need to check, it does not factor. So there are some ways to check that. One option is like, for example, you take this. uh, Okay, 1 second. Yeah. So you have this. Okay. So can you tell me what are all the roots? I'll tell you two explanations for this. But can you tell me? So root 2 plus root 3 is a root. Okay. Can you tell me other roots of this?
Root 2 minus root 3.
Root 2 minus root 3. Is it? Or maybe
No,
the,
no, no,
this
no.
I
Minus,
can do.
yes,
Yeah.
yes, yes. Minus
This
root 2
I can
minus root
for
3.
sure say, right? Because what you can do, you can if you put minus root 2 minus root 3, then this will be the same, because you are doing a even powers for x.
Exactly.
So you have two roots, but can you tell me other two roots? Okay, so let's okay, we don't know. Okay, so there is one option, I know, but I don't want to say that without explanation. So this could be x square plus ax square plus b, and you can sorry. So you have two. You could have cx plus d. You could have like this, and you
Yes.
can check that if this is possible or not for some a b c d. Okay. Okay. By
Okay.
rational root test, you know that by rational root test we know that uh, there is no linear factor, because there is no root factor
Yes.
in q. Okay, So the other option is 2 plus 2.
Oh,
Okay.
2 plus 2. Yes,
Yeah.
yes.
So that is one option to check, but I will not do that. Hard to check, I could say. I'll try to do with different argument, but keep it as
Mm.
an exercise.
And
Yeah. Hmm.
yeah, is it there is some theorem for any polynomial? If we have any polynomial of degree n, and
Hmm.
suppose we have a root, so
Hmm.
the product of the root is the constant term of the polynomial, and the sum of the root are the so the second term of the
Oh, okay, okay. So yeah, yeah.
It has
So
root theorem. It has root theorem.
yeah. So let's say alpha, beta, gamma, delta are the roots. Okay.
Exactly.
If these are roots, yeah, very good. So you have this. Then alpha plus uh, plus you have this should this is 0 because there is no
uh,
term of x cube, and product is 1 because that is from constant term. Will this be minus? So yeah, there are some things you can check. So what are we trying to do? If we know two roots, even we know that there are these two roots, so you have this and you add it to this. So from these explanations you could say that gamma plus delta is equal to 0. This implies gamma should be minus of delta. And from alpha beta, if this is 2 root this into minus, I'm just trying to do with this. What will be the sign? So I'm bad at this.
Minus, plus, minus, minus,
Is it minus? Okay.
plus. Negative cube term must be minus. Then cos square term plus and x term here 0. Again minus or again plus.
So this should be plus. Okay. Okay. Now this is 1, and you have minus delta square, and you can use 1 by, for example, root 2 plus root 3, and this is, yeah, minus is already there. So minus will become plus with this minus, and you will have something like that. And you can get delta like from, yeah, just rationalize it. So after rationalizing you will get something right there, like this, right? Yeah, very good. Yeah, this is of course very good. Yeah, other roots now you know. So gamma will be, let's say, this, and delta will be minus root 2 plus root 3. So you know all the roots. Very good. Yeah, nice. So you have all the roots now. So now what you can do, since these are the roots, again you know that we are in the field and we are in the UFT. So we are in the UFT, so that means this polynomial x raised to power 4 minus 10x plus 1 should split in the form like x minus root 2 plus root 3, x minus, so I'll just use plus here, and let's say root 2 minus root 3, and you have x minus root 3 minus root 2. So all the so this is plus minus root 2 plus minus root 3. Okay, all the options. Yeah, very good. So now you have this. Now what you can check, if there are options, so what you need to check, either this is there, either this is there, or this is there. You have to check all not just these. uh, yeah, so actually and with this only it is enough, because if one of the factor is there, then other factor will be there. So you can check x minus root 2 plus root 3 can combine with any 3 or not, with the coefficients to be in q, right? Because if we are saying that this is splits in quadratics, we should be able to write it in terms of quadratics. So this factor will be there in one of the quadratic, so that means this factor into any of this can you see that this gives the required thing. So that is one option, and yeah, and that is now beautiful to check even. So you can check if this is okay or not. which is okay to see by. It won't turn out, so you can keep it as an exercise also. Okay, so check. Very good, but this is nice in the sense now you can multiply, because here there will be so many calculations to do. Very good. So this is one option. The other option, why I'm saying that, because that will actually give two things that. So let's take q root 2 comma root 3. Now I am claiming that claim q root 2 is equal to q root 2 plus root 3. That is, this is simple extension of q. So root 2 plus root 3 is a primitive element of this extension. That is what I'm claiming. And if we do that, we can then we know that this has to be irreducible, right? If root 2 plus root 3 is the primitive element, then the extension has to, so we have this extension. So this extension over q, we know that is of degree 4. So this has to be of degree 4. So the minimal polynomial of root 2 plus root 3 has to be of degree 4. So that polynomial has to be irreducible. We cannot have two monic polynomials of degree 4. That is not possible. We have, for fixed degree, we have only one polynomial, if we are saying. Okay, because the divisibility property. So that has to be irreducible. So this will suffice, and even it will prove that this is a simple extension. Even before that also, because we are saying if there exists something of degree 4, like irreducible polynomial of degree 4, then it has to be same. So both of these are same things if we prove that polynomial is irreducible. So let's try to prove that, because even I can prove that this is equal to root p plus root q, again with some special conditions. So p and q are of GCD1, p and q are square free for that boundary conditions. Pq is square free, p and q are 1, and p and q is not equal to 1, because that does not make any sense otherwise. Anyway, that will be same, like if p is equal to 1, then these two ring fields are going to be the same. So let's try to prove that. So what I'll show that it is enough to show. Okay, so firstly, so to show. So firstly, q root p plus root q is always going to be in q root p plus root p comma root q, right?
Yes.
Right, very good. So that is always the case. So what we need to just check, if we can prove the other side. So what is the other side? So it is enough to show that any of these root p or root q belongs to q root p plus root q. Why? Because if I want this condition, so if I want this condition, if I show root p is there in q root 2 plus root q, root p plus root q, then since root p is there, so root p plus root q minus root p will be there, so root q will be there, so everything will be there. Q is already there, root p is there, root q is there, so that is the like smallest field. So this will have q root p root q. So it is enough to show that root p belongs to q root p plus root q. Is that okay, this argument?
Okay.
Okay, great. So let's try to prove that. So I'll do some that square thing again. So if this, so these are the same arguments, so to say. So this is even, so we don't need a polynomial here to even say that this is this has degree 4. So even we are doing some squaring and everything to get root p's there. So let's try to do that. This is equal to what? P plus q plus 2 root p root q. So what I can write, root p plus, so I'll not disturb this root p plus root q, because we already have, so root p belongs to this, that means we have the coefficients from here. Coefficient means elements from there. So root p plus root q is there in our field. So minus p minus q, since p and q are in q, we are okay here. Also we can divide by this, right? Now next step, what we can do, this by 2, and even what we can do, we can multiply by root p plus root q. So we have this element, so I can use this element because in the field we have root p plus root q, so I can use this. So you have multiplied by this, okay. So some argument only, so root p plus root q, I mean, should I assume? I can do that. Let alpha equal to root p plus root q, just for sake of writing. So alpha square minus p minus q. Alpha is just a number. You have alpha, and what will you get here? You will get p root q plus q root p, right? And now I have to get rid of root q. So what I can do, p minus q by 2 alpha. If I add, so I'll not add, I'll subtract. I just need to get rid of p into root q. What I'll do, uh, because alpha is there with me, so I'll multiply by p into alpha. So I'll get p root q plus q root p minus p alpha. And what is this? What will you get here? So p root q plus q root p minus, yeah, p root p minus p root q, because alpha is root p into root q, root p plus root q. So you will get here, this will get cancelled, and you can have q minus p, this. Since these are distinct, p and q, we are in good condition. So and you can divide by q minus p here now, okay. So root p is there. This implies root p can be written, since alpha is there, all the elements are in q, q minus p is non-zero, so this belongs to q alpha. So that is equal to q root p plus root q. And we are done. Is that okay?
Yes.
So now, very good. So now we have q root 2 plus, so in particular again, or let me write, this implies q root p plus root q is same as q root p comma q root q, and this is over q, this is over q, this has 4, so this has to be of extension 4, right? So this implies in particular q root 2 plus root 3 over q is of degree 4, and x raised to power 4, and mu of root 2 plus root 3, and this is also same as q root 2 comma root 3. This comma q is of, yeah, that is exactly x raised to power 4 minus 10x plus 1. Yeah. So far so good?
Yes, ma'am.
Okay, great. So we have degree 4 and extension of degree 4. Very good. Okay, so yeah. Now, so we have this extension to be simple, but what they have asked, let let us see. Minimal polynomial, we got a minimal polynomial. Is the field extension Galois or not? That is the question. So Galois extension means, again, for Galois extension, what do we need? The minimal. So now you know that is a simple extension. So again, for simple, what is the requirement? If we want to check that, we just need this condition. So we need, if minimal polynomial splits in the bigger field with linear factors distinct, right? So that we, because we are in simple case, because root 2 plus root 3 is our primitive element. Okay, let's check that out. Okay, we have this, and this is the minimal polynomial. Now we have already checked, since q root 2 comma root 3 is same as q root 2 plus root 3, this implies q root 2 plus root, this implies all the roots which we have already calculated, all the roots of mu root 2 plus root 3 in q are in q root 2 comma root 3, because roots are what? What are all the roots? We have already checked. Root 2 plus root 3, even plus minus I am writing. So okay, yeah, root 2 plus root 3 minus, if you get confused, I can also write like this. Yeah, some minus and plus, all the options. Okay, anyway,
All are
yeah,
distinct.
yeah, all distinct, and four distinct roots, four root, of course. So we have also basically mu root 2 plus root 3 comma q has simple linear factors. Simple linear factors means, simple means multiplicity 1 of all the roots. Simple linear roots in L. So what is L? L is equal to q root 2 plus root 3. So indeed this is a Galois extension. This implies L over Q is a Galois extension. Okay, very good. So this is a Galois extension. Okay, so we are done with this question. Let's move to the next question. Pencil is being charged, so I will write in few minutes, in 1 minute maybe. Let P and Q be distinct prime numbers. Is that okay? Any doubts?
No.
Okay. So let P and Q be distinct prime numbers, and let L is equal to Q root P comma root Q. So we have done this case also. Okay. So these are distinct prime numbers, then these are relatively prime. So good. These are square free. That is also good. So these are in the situation which we considered earlier. Okay. Now it has been asked, is the field extension L over Q a simple extension? That we already proved this is a simple extension, right? So this is, yeah, this is Galois. Now let's prove this. Actually we did already this part. So we proved that. So root P comma root Q, that is equal to this, proved in previous question. Okay, now let's see A part. Yeah, this is simple. Yes, simple, because we have just one generator with this. B part, not B part. Yeah, if the answer is yes, then find the primitive element. Yes, primitive element is, yeah.
We have discussed about primitive element in the previous section where the term was involved in the question. But primitive element means
Hmm. Yeah.
means it simply the only element can generate the extension field alone.
Uh, yeah. So primitive element means you can. So okay. So
I have not
this,
in
yeah,
the
yeah,
book. I
not
have
as
used the
vector
PPT.
space. So primitive element is by definition is the generator of is the generator of generate. So if this is L, then we will say L cross, yeah, L star. So by definition primitive element is the generator of L cross, means you should be able to so generate by this. Is that okay?
Okay.
So
Means it is a generator of the.
this is not a generator in terms of vector space. Vector space generation is different. Like you can write. So how shall I say this? So the point is, when you write vector space basis, you just need some element like. In this case, I don't know which option I should take, but okay. But what I mean to say, primitive element means it generates this L cross. Oh,
Okay.
oh, just 1 minute. Not this, like, should I write like this? No, 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 no. This is not finite, so I should not write like this. I want to say in some other sense. It makes sense, but let me write in some other way. Uh, so, mhm.
Means
Yeah.
nth root of the unit if a polynomial is of the form nth root of the unit. Then the generator of that group is the primitive.
Okay, nth. Yes, that is true, but that is also not. Okay, you are right, but I don't want to. Okay, so what I mean to say, yeah, you are right. You can take, for example, if you take this, then you need two elements. You need two elements, so it will split in this field. You need omega also, or maybe if you want, you can take just unity. But the point is, um, as a vector space, I want to say. Okay, let's not go into. Actually, there is this difference of vector space primitive element. We don't say that primitive element. So there is. So for example, you can choose 1 plus root 2. You can choose root 2. You can choose, for example, for this itself 2 plus root 2. You can have any element here. Okay, a- as a as vector space, if you want to write like a plus b and this element alpha, then it is okay. But here degree is 2, so we don't care about which element we are taking. But if we really want to write with which element it can be generated, then this is different. So here the case requires, I was writing in the sense of this, and uh, this does not make sense because this is not finite, so we don't write in the form of cyclic or something. Okay, that's why I'm avoiding writing this. But okay, let me just explain in just. I'll explain it next time with a proper example, because I need a example to say my thing.
There are no definition in the standard book like
Mm-hmm.
Dungeon book. I
Yeah, yeah.
have when I have confusion, I am just Google it and they are saying some different in a kind of way that it would leads against confusion.
Uh, okay, let me explain in this way also. So for example, if you take this, okay, and you take over q, okay, Now if you write it as a vector space, you can have you will say you will write like this, right? But this is not true, because we have this degree 4. You have to take a square, you have to take cube, and then you will say that you will search for the minimal polynomial here, right? But it could happen that whatever you are okay, let it be. I'll explain with an example, as I said, because I'll confuse you otherwise. I don't want to. Yeah. So for primitive element, just for the sake of primitive element, we will take only like q root p plus. So primitive element means you can write L to be like this, just this. Okay. Like this means smallest field generated by q and root p plus root q, or you can say smallest subfield of L
Content
q
Q and
subfield containing root p plus root q. Okay. This is the basic definition, and that's fine, because in terms of field you are allowed to multiply, you are allowed to divide and everything, so we are okay in this case. Okay. So yeah. Yes.
When L is a finite field, then the primitive element is the generator of the cycle, L field.
Yeah, it is the generator of.
Cyclic group, L group.
Yeah, exactly, cyclic group, but it does not make sense to say cyclic group here, right? Because we have q. So like if you say cyclic group is L cross. Every finite subgroup is cyclic. We don't say about infinite groups, so I don't want to go into that. That's why I'm saying.
Yes, yes, ma'am.
Yeah.
And
Okay.
yes, ma'am.
I'll give you an example of what I really want to give a difference. Like even that element, we say that I just forgot. So I'll give you an example next time for sure. So for now, primitive element, this is the definition, and that makes sense, and we know this already. Great. So we have this. Now simple is okay. If answer is yes, then find a primitive element. That we are done with that. So primitive means, as I said, this definition. Okay, and that is okay, because we have q, we have root p plus root q, so we have all the powers, all the multiples, so we get everything. Okay. Because we have seen that from root p plus root q we can get root p also with uh, this. Okay. Great. So yeah, so first part is done. Let's move to the B part. B says compute the Galois group. Now we need to calculate this Galois group and list all intermediate field of L over Q. Okay. So compute the Galois group means as we have seen that this is a Galois extension. So what is this? These are all the automorphisms, right? Automorphisms, Q algebra automorphisms of L. And what will be the automorphisms now? Can you so here is this extension, or we can say q root 2 comma root 3. So since you know that, you can have this, you can have q. Okay. So what are all the extension we need to see? And even this root 3 have this. This is some kind of tower. Okay. So automorphism of L, Q algebra automorphisms. So what are all the automorphisms we can check? From Galois extension and everything, we know that all the roots, okay, roots of any polynomial will map to the roots only under automorphism. Okay, so this is something we already did, like not already did, it is there in the lectures. And so in this, yeah, If L over K be a finite is a field extension, then this Galois group operates naturally on the zero set this of f in L. That means sigma of x. So sigma is the automorphism. Okay, sigma of x will always land up in the roots of that polynomial. Okay, so let's use this. And these are field extensions of field automorphisms. Okay, yeah. So we are saying we have q root 2 plus root 2 comma root 3, and even if we know q root 2 plus root 3. So this we have, and now can you, so we need to give a map from here to here, which is a q algebra automorphism. Okay, so let's try to so can you tell me where will it map, as we know this root result? So if I say root 2 plus root 3, then where should it map? We have a minimal polynomial of this, that is x raised to power 4 minus 10x plus 1, and we have all the roots of this also. So if I say this is f, v l, this is l, v l f, what do you have? Root 2 plus root 3, root 2 minus root 3, minus root 2 plus root 3, and you have root 2 minus root, yeah, both minus. So where should it map?
Other roots of f.
Exactly. So other roots are the choices. So you can have something, any of these four. Okay, any of these four. And you know that, you know operation how it is operating on this, then you know everything, because this is a field automorphism. Field automorphism means, firstly, this is a q linear automorphism. That means it will fix on q, and we also know that fixed field of L over this Galois group, because this is a Galois group, so it will be equal to q. So all automorphism will fix q for sure, and only those. Okay, so you have automorphism, and it is defined on the root of on x. So it is defined on everywhere, because this is field automorphism. So you have all the linear combinations, you have product. If you know x and y are going where, you can know, you will know x plus y is going where, and x minus, so if you know x and y going somewhere, so if you know where x and y is going, you have all the linear combinations, right? And even product. So x plus y is going there, we know. X into y, where will it go, we know. Even we know with any element of q, where will it go. So we know everywhere, right? So I'm saying, if we know where it is, so it is fixing q. Okay, q is going to q. Okay, as a set identity. Do you agree? So we know where it is going on q, and where it is going on root 2 plus root 3. So is this enough to define the automorphism?
Yes, because it is the basis element, and if we fix the basis element where up to they go,
Mm-hmm.
then we can find whole map.
So yeah, so basis element means, as I said again, here basis is 1, root 2 plus root 3 square, root 3 plus root 3 root 2 plus root 3 square, and root 2 plus root 3 raised to power 3, because we know that degree of minimal polynomial is 4. So on all four elements, if we know where it is going, then we are done, right? As linear or like vector space isomorphism, firstly, where the square go, this will come from field automorphism. Field automorphism allows you to multiply, right? So if x and y is going somewhere, we know that where x into y is going, that will go on the product of image of x and y, right? So we know where square is going, where cube is going. So if we know this from field automorphism, we know from the vector space isomorphism that where all the elements go. So yeah, both of these things. That's why I'm saying algebra automorphism is important. This is a field automorphism, and this is a vector space isomorphism. That is k-linear isomorphism, q-linear isomorphism in this case. So we know where sigma is. So we know just by q and root 2 plus root 3 where it is going. So we have 4 automorphisms. So we have sigma 1 and sigma 2, sigma 3, sigma 4. I can define like this. So we have sigma 1 from L to L, and this will map. Of course, we know that it is fixing Q. So first one will, let's say, it will go to this. Sigma 2. I'm writing this because I need one more step in this. So you have root 2 minus root 3. Let's say sigma 3 is L over this, root 2 plus root 3, where it is going minus root 2 plus root 3, and let's write sigma 4 here. Root 2 plus root 3 is mapping to minus root 2 minus root 3. Okay, so with this situation, can you tell me where root 2 is, where root 2 will go? Firstly, note that Q is going, so in every case, fixed field is Q. Fixed field of Galois group L over Q is Q. So fixed field is Q. So this is identity map, right? Because Q is fixed, and root 2 plus root 3 is also fixed. So everything is fixed, right? So root 2 will map to root 2 and root 3 will map to root 3. And one more thing, if you know where it is mapping to root 2 and root 3, like separately, then also you know where it is mapping. That we will require now. That's why I'm saying. So this data and this data is equivalent. Whether you give the data on root 2 and root 3 separately or root 3 plus root 3, these are same data to define what is the, because again you have all the operations and you know everything. Okay, here what will you say about this? Where will it map, root 2 and root 3?
Root 2 map to itself and root 2 map to minus.
Yeah, exactly. Actually, there is one more thing, and you can also check where will root 2 map and root 3, where will root 3 map. So one thing, so again we can use that data, like zeros of any minimal polynomial will map to the zeros of the same polynomial, right? So you have minimal polynomial to be x square minus 2. So mu of root 2 in Q is this. So zeros of this in L, okay? In L means again root 2 and root 3 all are there. That will be what? Root 2 and minus root 2, right? Because the roots are root 2 and root minus root 2. So root 2 is allowed to only map to root 2 or minus root 2. Similarly, root 3 is allowed to map to root 2, root 3 or minus root 3. And all the possibilities are there because you have all 4 options, right? So you have plus, minus, and here you will get root 2 will map to minus root 2 and root 3 will map to minus root 3. So you have all 4 possibilities, and so you have this data. Now so list all intermediate fields, and this is Galois group, okay, Galois group L over K, okay. So so this, so I'll not prove this, you can but I'll okay. so more generally, for pairwise relatively prime square free integers, if you consider this extension, then this is a Galois extension, first thing. So this is a generalization of root 2 root 3 thing. It is isomorphic to the group plus 1 minus 1 raised to power n. That means in this case where n is 2, because we have just a1 and a2, which is 2 and 3. So we should be able to prove that this Galois group is isomorphic to plus 1 minus 1 raised to power 2, and which is true. Why? Because what is the Galois group? You have Galois group of L over Q. You have 4 automorphisms. And where will it map? So you map it to plus 1 minus 1 raised to power 2. How will you map? So you just map according to where root 2 and root 3 are mapping, because that is enough data. So you can map sigma 1 will map to, so these are cross, okay. So 2 means this is plus 1, you choose cross plus 1 minus 1, right? So you have plus 1, you map it to plus 1 comma plus 1, this ordered pair because order matters here. And where will sigma 2 map? This will be plus 1 minus 1. You will have other option to be minus 1 plus 1, and fourth option is minus 1 comma minus 1. So this is indeed isomorphism, because these are the only 4 options. This is injective, bijective, so this is a isomorphism, okay. Isomorphism or isomorphism is groups. Why I am saying groups? Because this is a group isomorphism, because this is a group. You can write it to be there are 2 options. You say unities of Z, that is plus 1 and minus 1, or you can, that is also isomorphic to Z2 cross Z2. Okay, so this is isomorphic as group, because automorphism group is also a group, right? Automorphism group, anyway I'm saying.
But ma'am, Z2 contains 0.
Sorry?
Z2 contains 0 elements. So
Z2 is contained in?
0 element.
Yeah, so it's a isomorphism, so you can always define, you can yeah. So you can map 0 to minus 1 and plus 1 to, it's just how we are identifying isomorphism. Yeah. Okay. So we have this one more thing here. So in this case, this is isomorphic to this. Okay, where was the question? Yeah. So yeah, A part is done. This one. So similarly, you can prove for general thing. Just try to do that. If you can't, just let me know. I'll do it next time maybe. And there is one more thing. And when you do this, so furthermore, for each k, and we need all the intermediate fields. So what are all the intermediate fields from fundamental theorem of Galois theory? That is the fixed field of all the automorphisms, right? So fixed field of automorphisms means, so for this field we have fixed field to be, so from fundamental theorem of Galois theory, theorem of so you have sigma 1, you take the fixed field, so you all the intermediate fields are there is one correspondence between subgroups of Galois group. Okay, so I mean subgroups, not from sigma 1. So subgroups of Galois group, and so you take fixed field of H, okay, or I'll write subgroups of, so there is one correspondence between so this is M is which is contained in this, and so this is the correspondence. These are field. This is a field. Okay, so where M, how will you get a how will you get a subgroup? You will get it from this. So you will have L over M. Okay, this is also Galois. All the intermediate fields are also Galois over L. And from this side you can you have H. So when you take M, you can go there, and from H you can calculate the fixed field. You take H over L. So fixed field of L over H. So you just need to, now you just take what are all the subgroups you have. What are all the subgroups? Subgroups of this. Subgroups of, let's say, so you have sigma 1, sigma 2, sigma 3 and sigma 4. Okay, so so you can actually take the subgroups of Z2 cross Z2. So what are all the subgroups of Z2 cross Z2? You take okay, so in this term I'll write, so sigma 1 is identity, right? So identity comma sigma 2, because when you square sigma 2, okay, will you get, so sigma
Yes, ma'am.
yeah, sigma 2 of sigma 2, yes, you have sigma 1 sigma 3, right? So these are all the subgroups. And so operation is composition, right? So composition, automorphisms, operation is composition, and yeah, you just have all three, and the full space, and also sigma 1, and you have sigma 1 sigma 2 sigma 3 and sigma 4. So corresponding to that you will get, what will you get corresponding to sigma 1? So sigma 1 so sigma 1 is just identity, so fixed field of identity over L, you will get L, right? From this you will get K, because everyone is fixed, so everyone is fixed, yeah, you will get Q. K is Q. I am just calculating fixed field, right? Fixed field, so this is this calculation. Okay, so fixed field of, with all the sigma is, you will just get only Q. With sigma 1, because that is identity, everything is fixed under that. So from this sigma 1 and sigma 4, what was sigma 4? Sigma 4 is sigma 4 yeah, sigma 4 is minus root 2 and minus root 3. Oh, yeah, minus root 2 and minus root 3. So what will you get? Yeah, fixed field from this. So something should be fixed, right? Yeah, actually you will get this. You should get something like root 2 into root 3, because that will be fixed. So when you take root 2 and so root 2 is mapping to minus root 2, root 3 is mapping to minus root 3. So what will be fixed? Root 2 into root 3, right? This is fixed field of this sigma 1 sigma 4. Is that okay?
Okay.
Huh? So this is product. From here what will you get? From here you will get sigma 1 and sigma 3. So you have sigma 1 and sigma sigma 1 is again identity, sigma 3 is fixing root 3. Okay, so you will get Q fixing root 3 means this. From this you will get Q root 2. Yeah, so these are all, and these are all distinct, because this is a Galois extension. That's what it ensures. Whenever you take if it is a Galois extension, then you will get 1-1 correspondence, like there will be no repetition. It will be a bijective map between automorphisms and between intermediate fields. Is that okay?
Yes, okay.
So this is very strong, because otherwise it's very hard to find intermediate fields, because you never know what are all. Okay, but in this case, as you can see, you know everything, like you know on all. So all the automorphism. So that's why we this groups are used, and of course there will be so many applications of that, but this is one of that. Okay, so I'll stop here.